The last subject for today is talking about how to use flip-flops to create a binary counter. Now you'll remember that we've already talked about binary counters. They would count 0, 1, 2, 3, 4, 5, 6, 7, and then back to 0, for example. That would be a modulus 8 counter. Or you could have 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. That would be a modulus 4 counter. But essentially the job is that they count up to a certain number and then they go back to 0. And it turns out that we can do that quite easily using JK flip-flops. And we're just going to put every flip-flop into the toggle configuration. So j equals 1 and k equals 1. So this means that the output will toggle for each flip-flop with each active clock edge. So this is, remember when I said that the designers of the JK flip-flop were very clever? This is why they were clever, because this one application is really going to make good use of the toggle configuration. So let's look at figure 7. Figure 7 is a 2-bit binary counter. This will count 0, 1, 2, 3, 0, 1, 2, 3. We know that it's modulus 4 because there are 2 flip-flops, and 2 to the second power is 4. If there were 3 flip-flops, 2 to the third power is 8, and so it would be a modulus 8 counter, for example. So here's the really interesting thing. The clock only goes to the first flip-flop. You'll notice that these are always going to be negative edge-triggered flip-flops, or falling edge-triggered flip-flops. So the clock goes to the first flip-flop, which is in toggle configuration. This is just showing that the clear bar is disabled. So we've attached this to 5 volts, so that's going to be disabled. And then the output of the first flip-flop is going to go to the negative edge-triggered flip-flop or negative edge-triggered clock signal of the second flip-flop, which is also going to be in toggle configuration. And this is it. This is all the connections. We connect the output of the first flip-flop to the clock signal of the second flip-flop. And when we do that, this is the timing diagram that's going to result. So what we're going to find is that the clock signal, when we have an active edge on the clock signal, that's only going to trigger the first flip-flop. And it's always going to be in toggle configuration. So every time that an active edge occurs on the clock, we're going to get a toggle on Q1. So Q1 is going to go from 0 to 1, 0 to 1, 0 to 1, and so forth. But it's only then Q1 is going to count as the clock signal for Q2. And it's only on the falling edges of Q1 that Q2 is going to toggle. So we're going to see that although there's a transition here in Q1, it's the inactive edge, it's the rising edge, which doesn't mean anything to Q2. So we're going to see that only when there's a falling edge, only here is Q2 going to also toggle. So it'll go from 0 to 1. And again, here there's a rising edge on Q1. Don't care. It's sort of like reloading a gun. It doesn't do anything when you reload the gun. It's only when you shoot the gun that you're actually going to have something happen. So here there's a falling edge, and so therefore here there's going to be a toggle. What you'll see then is 2 things. First of all, the clock signal is going to be at a particular frequency. Q1 is going to have half as much frequency. Because remember that although there are 2 transitions here on the clock signal, it's only the falling edge transition, which is where we're going to see a toggle on Q1. So we go from clock to Q1, half as much frequency. Q1 to Q2, half as much frequency. So here you can see that there'll be four transitions in there'll be 4 periods in the clock signal for every period on Q2. So here's 1, 2, 3, 4, and in that same amount of time, Q2 only went through 1 full clock period. That's the first thing to observe, is that we have the halving of the frequencies with each step. The second thing to observe is that if we look at the numbers now, we have 0, 0, 0, 1, 1, 0, 1, 1. And those are the numbers, the binary numbers for 0, 1, 2, 3. And then we go back to 0, 1, 2, 3. So in fact, this does create a binary counter, exactly what we were looking for. And it's just about the easiest configuration we can imagine. You just simply put each flip-flop into its toggle mode. You make sure to deactivate any sort of clear bar or preset bar. You send the clock signal into the first one, and each time you send the output to the clock signal of the next one. Now here we've shown it for 2, but you can also have more than 2. And here, for example, I show 7 of them. So in this one we have 7 flip-flops, and in each case the output of each one goes to the clock input of the next one. And the output of each one is driving the clock input of the next one. The clock signal itself is only going to the first one. So this is going to be the least significant bit of the counter, and it's going to change half as often as clock. And this one is going to change 1/4 as often as clock, and 1/8 as often, 1/16 as often, 1/32 as often, 1/64 as often, 1/128 as often. So we find that this is going to be a modulus 128 binary counter. 128 clock signals are going to be necessary for this last bit to go through a full cycle from 0 to 1 and then back to 0 again. That means that the frequency of this output will be 128 times slower than the clock signal was. There are lots of times when this divide by 128 or divide by a big number would be very desirable. The numbers that we can divide by with this configuration are powers of 2. So you just say, what power of 2 is it that you want? Oh, you want to divide by 1024? That means you need 10 flip-flops, because 2 to the second is 1024. As an example of this, many quartz watches contain a crystal that vibrates at a frequency of exactly 32,768 hertz. They have used material science to very carefully design the crystal to operate at exactly that oscillation frequency. That signal is then sent through a chain of 15 JK flip-flops, shown just like the one above, and then that will divide that 32,768 hertz by a factor of 2 to the 15th power, and that yields exactly 1 hertz. So if you have a clock on the wall, or if you have a watch where you're literally seeing that the second hand is going tick, 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 if it's moving in very abrupt 1-second intervals, it's almost certain that there's a quartz crystal inside of it that's oscillating at 32,768 hertz, and it's then going through a digital device that's dividing that down by a factor of 2 to the 15th power to give that 1 hertz signal. In fact, the only time that you probably don't have something that has that quartz timing is if you have something with a continuous sweep hand. So if you see that there's a second hand that's continually sweeping rather than tick, tick, ticking, then it's probably a different way of keeping time. But most of the time, what you're going to find is this sort of configuration. So that wraps up today's new information. You have one more self-check example here of using flip-flops to create binary counters, and then I think you'll be ready to come to class.